Super. So, a lot of the stuff we're going to kind of jump around in section 4.2 and 4.3 tonight. I kind of move some like I'm going to teach it how I would normally teach this instead of necessarily the exact order that the book has it, but you'll get all the same stuff. So, the first thing we're going to talk about tonight is percentiles, quartiles, and box and whisker plots. So if you've ever, let's see, if you've ever seen something that looks like this, that's a box and whisker plot. And we're going to figure out how to draw them. Box and whisker plots basically allow us to organize data in a nice little chart. And it allows us to compare data because it shows us how much spread there is. So what we've been talking about up to this point is known as the measures of central tendency, which for some reason the book didn't use that name. That's mean, mode, and median. It's the stuff right in the middle. Tonight, we're going to start looking at how stuff is spread. All right. So because we can have two sets of data that have the exact same mean, mode, and median, but one data be from 0 to 100, and one set of data being from 0 to 100, and another one being from 40 to 60. And that 40 to 61 is a lot more compressed, so it's a lot more predictable than the 0 to 100. So we need to understand how things are spread and how that affects our data. That's actually where the majority of the stuff for statistics comes into play when you start to look at standard deviation, when you're starting to look at comparing data, when you're starting to look at things, seeing if things are feasible, those type of things, that all comes back down to variance and standard deviation more than anything else. So the first thing we're going to look at is spread. Step one. What is the range of this data? How do I find range? Right. So what's the range of this data? So it's 82 minus 18, which is what? 60 what? What was it for? Yeah, 64. Yeah. So my range is 64. That's one way we can actually look at spread. So the 0 to 100, this range would have been 100. The 40 to 60, the range would have been 20. So the smaller the range, the more compressed the data is. That's one way we can start looking at it. Another thing that we can start looking at to figure out where stuff is known as percentiles and quartiles. All right. You probably have heard of percentiles before. If you took the SATs or any of those, you got your score, and it told you what percentile you were in. And that's where your score ranked among everybody else that took that test. The other one that I've mentioned before is when you have a kid, you talk about babies, you're like, what percentile you are in height and weight. And you don't want to be in the 95th percentile for those. You want to be around 50. When you're taking the SAT, you want to be in the 90th, the higher percentiles. So the question is, how do we find that? So to find a percentile, all we're going to do is we're going to take, I want to use their formula, so. I'm just going to copy their formula because their formula is okay. It's the value you want. So that's the value. That's the number of values. And that's the percentile. Okay. So to find a specific percentile, this is the formula we would end up using. So let's find the 10th percentile for this data. How many numbers do I have there? Not the range, how many numbers? Right. Okay. I was going to say how long it took somebody to sit there and try to count them all before they realized just count the rows and columns and multiply. So we have 40 of them. So if I wanted to find, so I have n is 40, and I want the 10th percentile. So it's 10 divided by 100. So what's that equal? 4. So I want the 4th number. So I go,
Where do you get the 10th from?
I made it. I picked it. I'm looking for the 10th percentile. I could pick any number I wanted. I just chose 10. So the 10th percentile, or the 4th number, so I go 1, 2, 3, 4. So 27 is the 10th percentile. So at 27, oh, I lied. This book does it differently. You have to take, so if it comes out to be an integer, so like 4, you have to look at the 4th and 5th numbers. What's the middle of those two numbers? 28. Exactly. This one's exactly 28 because you add them, it's right in the middle. So my 10th percentile is 28. That means there is 10% of the data before that number, and conversely, what's on the other side of it? How much is after that point? 10% is before, 90% is after it. Okay? That's all it's doing, is it's cutting the percentage in that place. Okay? What if I wanted to find the 50th percentile?
You have to move back forward.
No. What's the 50th percentile? It's going to be 40 times 50 over 100, right? Which would be 20. So I'm going to look at the 20th and the 21st numbers. So I'm going to look at that number and that number. Okay? So 24, well, 54 and 54 is the same thing. So my 50th percentile is 54. What's that also called? That one has a special name. That's my median. That's the middle number. Your median will always be your 50th percentile because that means 50% of all
I'm
sides.
sure you're gonna get to this,
That's
but
okay.
what if, you said you get an integer, it's 2 numbers, but if you get like 4 points.
You just round up and you pick the next number. Yeah, so I'll do one of those in a second. Let me pick a number that's not going to work. It's be nice and even. Let's do the 30. Or actually, you know what? We'll do the 25th percentile. So 40. Oh, wait, that's going to come out to be, again, that's going to be 10. So let's not do that. Let's do,
37.
yeah, that sounds good. 37. So 40 and 37 over 100. That should not come out to be a whole number. As it comes out to be a whole number now. What does it come out to be? 14.8. So we're going to look at the 15th number. You always go up.
How do you get that so fast?
You use a calculator? You are allowed to use a calculator. I wasn't doing that in my head. So yeah, and you always round up. You never round down. So even if it was 14.1, I'd go up to the 15th. Okay, so it's not really rounding. It's always going up to the next number. So I'm going to take my 15th number. So 10, 11, 12, 13, 14, 15. So 46 is my 37th percentile.
And because it wasn't a whole number, we'd only look at one number.
Yes, you only look at the one number.
Oh, that's an L, right?
Yeah.
So will L and P always be the same number? Because 37.
Oh, no. Okay.
You know what I mean?
No. 15 equals 40, 37 over 100. That's L. That's N.
Yeah.
That's P. Huh? Was it a T?
T.
Let's see. What is it? A T? Nope. It's definitely an L. It's an L. I don't know. It's called the location of the percentile. That's why they used L. But it's definitely an L. It's a cursive L. The only reason I'm using their formula is because I don't want you to look at their notes and then go in their questions and goes, what's that? Otherwise, I would not have used their letters. So yeah, it's an L. All right, so no, it's not the same. L is 15 in this case. Does that make sense?
2.5.
Yes.
Got it.
It's the 37th percentile is this formula, which gives me the L. All right, you can do this for anyone, any percentile, and it works for anything. So like when you got your SATs, if you were in the 83rd percentile, this is literally how they did it. They took your score and figured it out the other direction, basically, which you could also do. So let's take, if I can erase that because that's already there. I want to know what percentile 61 is. What's the location of that one?
I said it.
Yeah. So so that's 27. That's the location. I know there's 40. What I don't know is the percentile. Okay. Now we get to do a little algebra, but it's simple algebra. We're just going to take 27 times 100 and divide by 40. You just take it and flip it over. So it's 27 times 100 divided by 40. Somebody with a calculator. Otherwise, I have to take out my phone. 67.5? That's all
I
right.
was talking about the 61st or percentile or
No. So, okay.
unless I must have said it.
There's two different things. So depending on the direction you want, so if they ask you for the percentile, so the first one we said, I want the 37th percentile. And we found out it was the 15th number, which turned out to be 46. That's the 37th percentile. Okay. The other thing that you could do, so like the SATs, you got 950. What percentile are you in? So I know my score. I'd have to go backwards to find the percentile, right? I don't know that X. I don't know the P. So I'm looking for this now instead of the answer. So I know that's the 27th number in my list. So that's the L, because that's the 27th place. I still know there's 40 numbers. I'm looking for that. So to do the algebra to get back to the X, you just do the opposite. So instead of dividing by 100, I multiply by 100. Instead of multiplying by 40, I divide. And that gives me that X. That gives me my percentile. So it's the 67th and a half percentile, which they would call the 67th percentile. Because it's always a whole number. Does that make sense? Yes? Okay. You want to do another one of those? We're percentile 77. Uh, So we have, what's this, that's in what place? You're right, it is 37, so I messed up. I did 36. So it's the 37th place. So same thing as 40, and it's x over 100. So it's 37 times 100 divided by 40. So x is 92.5. So it's the 92nd percentile. If you said 93rd, I give you that one too. It's yes.
I think I might be doing something wrong because the numbers like seven, starting at like 77. So I did 40 times 77 divided up.
Okay, so the mistake you're making is you're using the number and not its location. That's why it's an L and not the number. So I don't want to use 77. I need to know where it is within the 40 numbers I have. So it is in the 37th place. So if I listed them all out, it's the 37th number in my list. That's why I'm using 37 and not 77. Okay? That makes sense?
Yeah.
Okay. Because remember, percentile is telling you where you are in terms of the rest of the information. It's not telling you what your number means, it's telling you where you are in terms of that thing. So if I took all your ages and listed you, where are you in terms of your age, in terms of this class, not overall?
Okay, so like where did the 77 go where the L is?
The 77 is not going to go where the L is. 37 is going to go where the L is because it's the 37th number.
Oh, like on the chart. Oh,
Right.
Oh.
A different chart would give you a totally different thing for 77.
Gotcha. It's literally the 37. Okay.
Correct. It's literally the 37th number.
That makes sense.
Okay. All right. So now here's I think we already found this one. That was 54. Find me the 25th percentile and the 75th percentile. It's okay.
I can't find a 24.
No. Okay. So this is the other one. So I'm giving you the percentile.
Oh, okay.
So this is this. So I'm giving you P. You need to find L.
Okay, gotcha.
And then you're going to count that many places, and that's going to tell you the number that you're going to use. And remember, if it comes out to be a whole number, use that one and the next one up. If you remember finding median in elementary and middle school, if there was an even number of ones when you counted to the middle, you found the average of them. That's why if it comes out to be a whole number, you're looking for the average of those two numbers. So what do we get?
I got it. 41. Is the third answer?
Wait. So 10th, 41, and 45. Remember, or no, that's 43. By the way, that's not 45, it's 43. So it's the 41. Remember, it's a whole number, so you take that one and the next one up.
Okay, so the number would be in between that.
Right. Correct. Yep. All right. So your 25th percentile, you should have gotten 10, which means you look at the 41 and the 43, which should give you 42. And the next one up. Yeah. So remember, it's just, remember like the median, where if there's two numbers in the middle, we have to add them and divide. Same concept. You're going from each direction to that point, and you get two different numbers because it's a whole number. Because like if you counted 10 up here, but if you counted 30 back, you're going to get to that number, not that one. So you take both those numbers, add them up, and divide by 2. Now, if you did the 75th one, you'd have gotten the 64 and the 66, which gives you 65. Is your 75th percentile. Yeah. Always do that number and the next one up.
Okay, wait, did you do 75? I don't know why my.
You got 30. You should have gotten 30.
I am not getting 30.
Because 40 times 75,
Never mind, I wrote things down wrong.
Okay. I was going to say that should have been 3,000.
I divided by 50 instead of 100 for some
There you
reason.
go. That'd be why. All right. So what does 25, 50, and 75 have in common? Not the answers, the actual numbers I just said. They're quarters. These are known as quartiles. Okay? So 25, 50, and 75 are special because they're quartiles. This is what we're going to use to be able to split the numbers into pieces to make my box and whisker plot. Okay? So we actually can make my box and whisker plot for this now. I should register that. This is what quartiles is, 25, 50, and 75. We'll deal with the other thing in a second. So 25th was, what was that number? 42? 50 was, what was 54? And what was 75 was 65. Okay. So when we make our box and whisker plot, this is known as Q1. That's my median. And that's Q3. Okay? Median or Q2, depending on how you want to say it. You never say Q2, you always say median, because that's the median of the data. So if I was to draw my number line, what was the smallest number? 18, right?
Yeah.
And the biggest number was 83? Was it 82?
Yep.
That was 82. Okay. Okay, 25, 35, 45, 55, 65, 75. Okay. Quick and dirty number line. All right. When you're doing your box and whisker plot, there's 5 numbers you need. Q1, Q2, and Q3. Q1, the median, Q3. The minimum and the maximum. Okay? So my median was 54, so I put a line at 54. My quartile 1 was 42, so I put a line at 42. My third quartile is 63 or 65, so I put a line there. And I make my box. That's my box. Okay? Q1, the median, and Q3. Yes, no, we're good to there? Okay. My whiskers go to my min and my max. So my minimum was 18, right? So 18, that's my minimum. And my max was 82. That's my maximum. That's a box and whisker plot. Okay. So your 5 number, they actually have a nice little, every so often they have nice little charts that give us the information that we want. And this one, they actually do have a nice little procedure for it. Yes, I am recording this. Yeah, if you see the little red dot at the very top of the screen, I'm recording. People still writing, so I'm going to give them a second to finish writing this one down. Then I'm going to put the procedure up so that you can copy down. Sure. So if you want to start listening, and then I'll switch over to thing. First thing you do is you determine your 5 numbers. Q1, Q2, the median, Q3, those 3 numbers. And you can do that using the percentile formula we just did. So what's the one thing you have to do before you can even find median? All your numbers have to be in order. I gave you a chart that was in order, so you didn't have to worry about that part. It's true for any percentile. If your numbers aren't in order, it doesn't work. So you have to have all your numbers in order. Find your Q1, your median, and your Q3. Find your min and your max. Those are your 5 numbers. Okay? Min, Q1, median, Q3, max. 5 numbers. Draw a number line or sketch a number line. Doesn't have to be perfect. Draw your box in the middle for your Q1, Q3, your median lines in the middle, and then draw lines going out to the mins and maxes. That's it for your 5-number plot. That is considered a 5-number summary and a box and whisker plot. And it's called a box and whisker plot because it's a box with whiskers. The one place that you actually do normally see box and whisker plots is in stocks. You'll typically see them when they look like this. Actually, I'm going to switch for 1 second. This is like what you'd actually end up seeing in a box and whisker plot. So we've got the information. So these are 3 different ways. This is the data for, I don't know, whatever they were talking about in this case, how long it takes to produce something. So you can start to look at how you can compare the quality or the time that it takes for these lathes to work in this example. So this one, these are a lot more compact than that one. Okay. So that's where, remember we were talking about spread, variance, and how things are moved apart. We can start seeing that this one and this one, we're going to get a lot more reliable data from. It's going to be almost the same every single time. Where that one, it's a lot more spread out. It has the highest point, but it also has the lowest point. So it's a lot more spread out. So you can start to look at how that box and whisker plot can show you that spread a little bit better. Does that make sense? And then the little yellow dot in this one is actually the median. They didn't put a line in the middle of this one. So if you were looking at a stock and you wanted to, if you're in your 50s, what kind of stocks would you be looking for? Ones that are going to give you a consistent return, or ones that could give you an amazing return or lose you a lot of money? Yeah. Yeah, you want to be consistent because you're getting close to that retirement. You don't want to lose your money, right? If you're in your early 20s, you might want to take that risk and go for that high end one. So it's not always necessarily the spread is what you'd want. Like you're going to use that data to determine your risk aversion in that situation. Yeah. So it's really one of those things that you want to look at your risk aversion. And that's what that box and whisker plot does, is it gives you a picture to show you that really easily. Okay. All right. We've talked about outliers, right? Things that can cause data to be skewed. What's the one thing in the central tendencies that is most affected by an outlier? So what are the 3 measures of central tendency? They're your 3 M's. Yes, mean, mode, median. Which one's affected by an outlier? Mean. Okay, mean's the one who gets pulled, right? So we want to know where those outliers are. And if we can, eliminate them as much as possible, right? By doing that trimming. This is why sometimes I'm not liking this book, because they talked about outliers, but then they didn't give you a definition of what an outlier is. There's an exact definition of an outlier. An outlier is 1.5 times the interquartile range. Okay. Hold on, I'm just going to get the numbers real quick. 42, 54, and 65. All right, so for my data that I just did, that's my 25th, 50th, and 75th percentile, my Q1, my Q2, and my Q3, right? When we found range, we went from the highest number to the lowest number, correct? If I'm going to look for interquartile range, I'm going from my Q1 to my Q3, because that's inside the quartiles. Okay? So what's the range from 65 to 42? No. The range, remember, range we're subtracting, the highest and lowest. So 65 minus 42 is 23. So my IQR is 23. So my interquartile range is 23. Okay? Does that make sense? So range is from min to max. So in the other one, this one, I think it was 64 because it was 82 minus 18, and there's 64. My interquartile range is just the inner box. How big is that inner box? In this case, it's 23 places. Okay? All right. So according to the definition of an outlier above, it's 1.5 times that. So what's 1.5 times 23? What's 1.5 times 23? Okay. So I'm going to add 34.5 here, and I'm going to subtract 35.4 here. So this one goes up to 99.5. And this one goes down to 34.5, not 35.4. 30 minus 34.5. 7.5 or 6. I swapped the numbers. It's 34.5, not 35.4. No, you're fine. I switched them when I wrote them. I think it's 7.5. So if I have a number that's lower than 7.5 or higher than 99.5, it is an outlier. Okay. In this set of data, do I have a number that fits that bill? My lowest number was what? 18. So nope, it's not lower than 75 or 7.5, so it is not an outlier. My highest number was 82. It is not higher than 99.5, so it is not an outlier. So this data does not have an outlier. Okay? I need a problem with outliers. Really? And they don't give you a single problem with an outlier. All right, so I can't come up with a problem quickly that has an outlier. Does the concept of the outlier make sense? That's how we can determine it. So if it's anything that's more than 1.5 times the interquartile range. Now, a lot of times you can look at the data and figure out like, yeah, that number is way out there. Okay. And you can count it that way. You don't necessarily have to look at it this way. But sometimes there's numbers that are pretty close that you really don't know. And the way the interquartile range works, it could still be on the outside. Because you could have two numbers. Like I could have had a number that was at, I could have had like 97, 98, and then 100. Depending on if it didn't really impact my interquartile range any, because those are just three numbers up there. The 97 and the 98 are actually part of it. The 100 is an outlier. So you might have saw 97, 98, and 100 and not think any of those were outliers. But the way the process works, that 100 would still be an outlier in that situation. Okay?
When it comes to tests and stuff, are we gonna have to like combine things like finding the outlier and then going in and getting rid of it?
No.
I mean, I probably could do it. I could do that if you had us just.
No.
Combine.
Honestly, like if I was going to ask a question like that, I would say, here's a data set, create me a box and whisker plot, find any outliers, which that you would have to do. That's all basically we just did here. Then I would ask a question, find me the 10% trimmed mean. Taking into account that I know there's an outlier, and that would take care of the one outlier that I had. So I wouldn't ask you then to figure out what the percent that you'd have to take to trim off the outlier is, because we haven't done that. That's a little more extreme measure of doing them. So that's, if I was going to do one like that, that's how I would do that. Okay. All right. Any question with box and whisker plots and outliers? Okay, good. Now on to variance. The book covers something known as mean absolute deviation. I have not checked the quiz, the actual section yet to see if they really do a bunch of problems on it or not. I'm not covering it. If it does, I will take that question out. I will look at that tomorrow. Okay. So if you happen to do section 4.2 before I go look at it tomorrow, if there's something with mean absolute deviation on it, it'll be gone. So you just give it a minute. So we were talking about the box and whisker plot and looking at how things are spread and how we can use that data to compare things. There's two different methods to find variance. A cheap method was known as the mean absolute deviation. It was to look at how things were, how far away from the mean they actually are. I'm just trying to scroll back to get the actual data set that I can use. It's just taking forever.
Wait, what?
You
said we're doing like variance
Yes.
right now? Okay.
All right. So we're going to look at this set of numbers. Yes, there's only a few numbers on purpose because the process actually is a longer one, and one that I'm not going to have you do by hand, except for right now. Because doing this for more than like 10 numbers is insanely painful because there's a lot of steps to it. I want to do this out by hands so you can see how to do it, so you understand what it's actually doing. Because just getting the number, which you're going to use a calculator to get the number, won't really get you an understanding of what it means. Okay, so we're going to do this once, and I'm not going to expect you to do this out by hand again. All right. The first thing everything is how far things are spread from the mean. Because remember, the goal, if the data is right, the median and the mean should be right in the middle together, right? So we want to look at how far things are spread away from them. So I need to find my mean. I'm going to put these numbers in order to make my life a little bit easier now. So I'm going to have, so I have 5, 7, 9, 9, 10, and 11. All right. Add them up and divide by 6. What do you get? 8.5. Good. That's not that bad. All right. I want to now find out how far each number is away from my mean. Because remember, we're looking at spread. Okay, we're looking at variance. So spread, variance, like we're looking at how far the information is apart from each other. So I'm going to subtract every number. I'm going to subtract 8.5 from every number. So this one is at negative 2.5, negative 0.5. This one's at 0.5, 0.5, 1.5, and 2.5. Okay. So right now, I know how far each point is. Did I wait? Oh, sorry, that's 3.5, not 2.5. Simple subtraction screws me. You're right, it is. Any of the other ones I screw up? I got all the positive ones right? Okay. So that's going to tell me how far each number is away from the mean. But I want to know the data as a whole. Right? So the next thing I'm going to do is to find what's known as my standard deviation. Which is the main thing that everything else after this point is going to be pretty much based on. Okay? We're going to square each of these numbers. Okay? So square them. So what does squaring them mean? Yep, multiply by themselves. So we get 12.25. .25, 0.25, 0.25, 2.25, and 6.25. Okay, 2 more steps. It is. This is why I'm never going to have you do this out by hand. it's just not going to happen. You're going to add them up. Yep, add up all the squared ones. So in essence, huh? No, because what's a negative times a negative? So that's actually the reason we square them. So mean absolute deviation actually takes the absolute value of them to get rid of the thing. Then standard deviation squares them to get rid of the signs. So yeah,
How would I do something on square root on the calculator?
it's the check mark symbol.
All right.
So you're gonna what? No, not square root. Squaring them, not square rooting them. So it's a little. It's the little 2 up top. All right. So add them all up and divide by how many I have. So you're finding the mean. You got what? I hold on a second. Yeah, 23.5.
Oh, okay.
Yeah. So you added them all up. So you got 23.5. Now divide it by 6 because there's 6 of them.
So like
You're finding the mean of them. So 23.5 divided by 6. I don't know, calculator. And you get 3.9.
That's standard deviation.
Almost. That is variance. That's known as your variance. Standard deviation, we squared it, right? How do you get rid of a square? We square root it. To find your standard deviation, you have to square root that. So square root of 3.92. Now you're going to use that check mark symbol. And you get 1.98. And that's your standard deviation. Okay. So what standard deviation does is a whole bunch of steps to tell you how spread your data is. Okay. So in this case, my standard deviation is 1.98. I told you I'm only going to have you do this once because we have calculators that do it for us. Okay. Now, I cannot so for anybody who's going on, okay, I cannot honestly believe any other teacher will ever make you physically find standard deviation out by hand. They might make you get the software to do it. The MATLAB and stuff like that will actually do it. They might expect you to be able to find it on a graphing calculator or a calculator that you actually have. And some calculators can do it. Some calculators can't. So you have to find one that has the stats option on it. A lot of the scientific calculators do have that feature on there. For here, just type in Google standard deviation calculator. This is the one I'm going to link on my website. But if you type in standard deviation calculator, this is one of the first ones that comes up. Yes.
Your standard deviation, take the original numbers that you subtracted, right?
Yep. Square them.
Square them and then square root them.
Well, you find the mean of them.
So you square root the mean.
Yes. Yeah. You find the mean of them and then square root the mean. So for this one, all you do is literally type the numbers in. You have to answer the question: is it a population or a sample? What's the difference? Right. So if I was going to do something for the whole school and I took you guys, you'd be a sample. The population would be the school. If I was just doing something for this class and I looked at all of you, you'd be the population because I'm taking all of you. Okay. So if you have all the data, it's a population. If you don't, it's a sample. It does change the formula a little. Okay. So it does change your answer a little. So just keep that in mind. And then you just hit calculate and it gives you the answer. So in this case, my variance is 3.91, which we got the 3.92, and my standard deviation is 1.98. Yes.
So variance and standard deviation. Obviously, like we did all of math. We know how to do them. What are they? And I know you mentioned they were like,
I'm going to show you.
okay, cool.
That's next.
And we don't need that formula, correct?
You will not need the formula. No. I'm not like, if this was a calculus-based statistics class, absolutely, I'd expect you to know that formula. My calculus class, they actually have to derive that formula actually using integration. But in here, no, you're never going to actually use, and even if you get out, they always use computers to do it, either Excel, you can do Excel, Google Docs, any of those will do this real quickly for you. So there's no point in doing this out completely and utterly by hand, ever. And any teacher who tells you that is lying. All right, I need to find something real quick. I want ones that vary. Seriously, this is the things that drive me nuts because this book should have this exact thing in here and it doesn't. Perfect. This will work. Okay. So this is what standard deviation does. Not the greatest graph in the world, but it'll work for what I need. Okay. All right. So here are three what we would call, and what you're going to really easily know, these are bell curves. Okay. They're perfectly symmetrical. That's the key piece to a bell curve. It's got to be symmetrical. It's not skewed one way or the other. The middle, the mean and the median are right in the middle. All right. The blue one is a standard deviation of 1. Okay. As the standard deviation gets smaller, this red curve is a standard deviation of 0.5. What do you notice happens to the bell curve? It compresses. The data is not as spread. Okay, so the smaller the standard deviation, the more compressed the data is. Okay, the bigger the standard deviation, so this one is a standard deviation of 2, the more spread out the data is. Okay, so if we look at two sets of data, one has a standard deviation of 3 and one has a standard deviation of 500. The one with 500 is a lot more spread out than the one with 3. Okay, so the 3 would be more reliably, you'd be able to guess what the answers are going to be. It's going to be a lot more compact. Where the 500 is going to be all over the place. Okay? Does that kind of answer your question what standard deviation is?
Yeah.
Okay. I'm going to say, because if not, I'm going to have to try to come up with another option, and that's really the best explanation of it. So yeah, standard deviation really just tells you how far things are spread apart. Right? So why do we care how far things are spread apart? That's the next wonderful question. Well, because standard deviation gives us a very important rule called the empirical rule. And I'll copy and paste this one. So this one's nice. So the empirical rule states that 68% of all of the data of all your numbers will be within 1 standard deviation of the mean. Okay, so remember we were talking about percentiles and stuff before? Within 1 standard deviation, plus or minus that, 68% of all the information will be there. 95% will be within 2 standard deviations. And 99.7 will be within 3 standard deviations. All right. Everybody got this down? I'm going to show you a graphical representation of the exact same thing in a second. So, and then I'm going to tell you why this is important. So here is the bell curve with the actual percentages on it. So you can see it's the numbers are slightly off. It's 68, 95, 99.7 is approximate. So here's 1 standard deviation. So we're 1 out, 2 out, and 3 out. Now, that's not, so when I'm saying 1 standard deviation out, that is not the number that we just found. That's not what the standard deviation is telling me how far it's spread. So 1 standard deviation of that other one would be 1.9. 2 standard deviations would be 2 times. Okay. Anybody know the average height of a male in the United States? Almost 5'10", 70 inches. So it's 70 inches. That's the mean. And the standard deviation, which is that funny little symbol there, is 3 inches. Okay? So average male height in the United States, 70 inches with a standard deviation of 3 inches. So this is 70. 1 standard deviation would be plus 3. So that's 73. Okay? Going down 1, that'd be 67. So between 67 inches and 73 inches, what percentage of men in the United States are that height? 68%. 1 standard deviation away from the mean is between 67 and 73. Does that make sense? Okay. 2 standard deviations, we do it again. 76 and 64. So now we've got how much of the percent of the population? 95% of the population of men is between 64 inches and 76 inches. Now we do it again. (61 to 79). So 99.7% of the men are between 61 and 79 inches tall. Okay, which would be 6'7". Huh? 61? 5'1". Yeah. Okay.
Like 3 people in my host family are like.
Okay. Anybody know how tall the door is? Anybody want to take a guess? The door?
I guess about 80 inches.
It's exactly 80 inches. Code for doors in the United States is exactly 80 inches.
Where do you put all this in your?
Yeah, I was like, where did
Why can't you just randomly like a widget, like pull it out?
So, well, let's see, I taught in the tech schools for years and had to teach electricians and carpenters and stuff like that. So that type of
Oh,
stuff,
okay.
I know.
Makes sense.
But why'd you say 80?
because the thing that's 79, so I think you're rounding it up is just the logical decision.
Well, look at it. What percentage of people is after that? 0.1%.
Yeah.
That means 1 out of every 1,000 men would bump their head. Okay? So when they're designing things, doors, elevator weight limits, and all this stuff, this is what they use. This is how they figure out where those things are. Okay? So that this is why standard deviation is so important, because there's so much stuff that you do on a daily basis that they did this to figure out why those things are that way. Okay? So this is what standard deviation is. That's what it means with why we found it that way. Okay? We're done tonight. I'm not totally done with 6.2. You can do not 6.2. You can do 4.3. 4.2, I'm not done with yet. Okay? We will finish 4.2 on Thursday. Because I saw a couple more little things to do with this. So you guys can understand a little bit more about that. And then we're basically done for the test next week. Okay? Sorry.
But I get it. I think I get it. I get it.
And what the nice thing about it is everything we're doing from this point forward is basically going to tie back into this. So by the end of the class, standard deviation stuff is going to be a piece of cake.
I mean, if someone asks why it's important in their life,
There you go. It's like, honestly, there's certain things that like instantly, this is why it's important.
Before they had standard.
Yeah.
So every doorway and every window is a different size.
Yep. And your stairs are tight.
Actually, no.
Oh, they fixed the stairs?
They're just not tight.
know.
But, so the problem is when we get a new refrigerator, we have to go, instead of just like going like that to the kitchen, we have to go like,
Yeah, to get through doors. Look at your slide.